University of Tokyo. He will speak about the Ibragimov-Khasminskii theory and all the recent developments in statistical inference for stochastic processes. Professor Yoshida, it's now yours. It is okay for you? Nakahiro?
Oh, I'm sorry, I reset. Please wait.
Yes, we can.
Is it okay?
Yes, we can see your slides now.
Okay, I do it with it. Okay. So, thank you, Alexander. Good morning and good afternoon and good evening from Tokyo, everybody. Yeah, the warmest birthday wishes to a great leader. Happy birthday, Professor Khasminskii. When I was, when I was a graduate course student, yeah, maybe it is around 35 years ago. So for me, it is very long. Many years ago, one day my supervisor recommended I read your papers with Professor Ibragimov. I don't know, I don't remember exactly what I was trying to do with the Ibragimov-Khasminskii theory. I don't remember what I was doing, unfortunately, but maybe I was trying to study model selection problems. I think so. So I don't remember what I was doing, but of course it is true. I was very surprised with their beautiful theory and convergence of the likelihood ratio random field. Really, Ibragimov-Khasminskii theory gives LP boundedness of estimators and also a very clear perspective to analysis of Bayesian estimators. Today, Bayesian methods are unavoidable everywhere in statistics. I cannot imagine recent developments in theoretical statistics without their theory. I think so. I'm working in statistics for stochastic processes, and their ad hoc methods are rarely successful. So we need very universal and very strong methods. So in this sense, without doubt, Ibragimov-Khasminskii theory is one of the very fundamentals in our field. I'd like to sincerely express my gratitude for your constructing such a very deep theory, now supporting modern theoretical statistics. And also, it's a great honor to talk here. So I thank Yuri and the organizers for this precious opportunity. Thank you very much. So, yeah, please let me start with the very basic concepts of Ibragimov-Khasminskii theory. Maybe everyone knows here, but please allow me to start with this slide. The likelihood ratio field Z and U is defined in this way, and they showed convergence of random field Zn to some random field Z, maybe in some continuous function space C hat. And what is beautiful is from this convergence of random field, it is possible to give asymptotic behavior of the estimators in very unified way. And also their strong point is the theory gives the convergence of moments of estimators. And then a large deviation estimate for random field ZA. We shall discuss this point later. And, why convergence of moments? Of course, it is used in asymptotic decision theory, and there we need convergence of risk function. So yeah, we really need convergence of moments of estimator. Besides, in information criteria, yeah, for example, if we consider RK-90 information criterion, the correction term of AIC comes from convergence of quadratic form of estimator. In this case, maximum likelihood estimator. So for rigorous mathematical validation of AIC, we need convergence of moments. And it is also the case in asymptotic expansion. Yeah, for example, if we consider a process with small diffusion, satisfying this stochastic differential equation, here you see epsilon is small parameter in front of diffusion coefficient, and time horizon is fixed, but epsilon tends to 0. So it is called small diffusion. In this situation, we can derive stochastic expansion for maximal likelihood estimator, or more rigorously, the error, scaled error of maximal likelihood estimator. It is like power series, and R epsilon is a residual term. It should be small because it is residual, but proof of this fact. Yeah, for example, we need LP boundedness of, yeah, in this order, of course. We need such estimate, but it is not so simple matter. But Ibrahim-Khasminskii theory successfully gives such estimate because residual term is something like polynomial of U hat epsilon, and their theory proves LP boundedness of U hat epsilon. So once such a strong mode of convergence of this expansion is established, after that we just apply smooth function G to U hat epsilon and taking the expectation to get asymptotic expansion of the maximum likelihood estimator. If my memory is correct, such stochastic expansion was first derived by Yuri. Maybe, yes. And such LP estimate in his textbook. And so we can derive asymptotic expansion of maximum likelihood estimator. Yeah, here is second example. We consider Ito process, but in this case, we have a known parameter theta in diffusion coefficient. And capital T is fixed, but on the other hand, we have high frequency data. So that means that we have data of process X and Y. So these are observed at discrete time points Tj. Tj is J times H, and H is T over N. And N tends to infinity, so we have a finite time horizon and high frequency data when N tends to infinity. And in this situation, we want to estimate the value of theta. But yeah, as you know, in general, it's difficult to obtain the exact likelihood function for theta. So we take a quasi-likelihood approach. but quasi-likelihood approach we take, but even there, Ibragimov-Khasminskii theory will work very efficiently. So first topic is Ibragimov-Khasminskii theory for quasi-likelihood analysis. We start with a general setting. So omega is a sample space, and the theta is a bounded open set in RP. Of course, this is parameter space. And suppose we are given some random field Hn over theta. Our inference will be based on this random field Hn. An is a scaling matrix, and as usual, we introduce local parameter u around the true value theta star of theta. Un is a new parameter space for local parameter u. Then, following Ibragimov-Khasminskii theory, we consider quasi-likelihood ratio process ZNU. Because Hn is something like a quasi-likelihood function, so we take exponential of the difference of two values of Hn to make random field Z. Here, we assume Zn is locally asymptotically quadratic. That means Zn admits this expression. So Zn is exponential function of a random quadratic function in U. Here, delta n is a random vector, and gamma is a random bilinear form. So gamma is random in general. And this is inner product between delta n and u, and this is in a sense inner product, but this is nothing but quadratic form in parameter u with kernel gamma. RNU is a residual term. Of course, we expect Rn tends to 0. Yeah, because we assume local asymptotic quadratic structure, so this means in a sense, this formulation is very limited, restrictive, because this assumption is almost assume that differentiability, so smoothness of experiment. But still, it is useful in many situations. So we assume Zn is locally asymptotically quadratic. And also, we assume polynomial type large division inequality for Zn. Here, V and R is a collection of U's bigger than R. Okay? So this inequality says the tail of Zn is very light. Moreover, we assume delta n gamma tends to delta gamma. Then under this convergence, we get convergence of random field Zn to random field Z. But in our situation, the structure of Zn is very simple. So the limit is very simple. Zn is nothing but exponential of quadratic function. Because gamma is random, so this is, how to say, this is mixed normal Gaussian shift experiment. That's all. Yeah, of course, with respect to Hn, we can define quasi-maximal likelihood estimator by maximizing Hn with respect to theta. And also, the quasi-Bayesian estimator QBT is defined by random field Hn theta. In summary, yes, we have random field Hn, and we assume this one is quadratic, locally asymptotically quadratic. And for Hn, we consider random field yn. Bn is some constant tending to infinity, and if so, we will assume the following: yn converges to some random field y in some sense, and also we assume the following identifiability condition expressed by this inequality. This equality is trivial, so the assumption is here, and the rho is some positive constant, and the chi0 is random variable. And if chi0 satisfy this stochastic non-degeneracy, then it is possible to prove polynomial type large deviation inequality for random field Zn. And so by Khasminskii theory, we can obtain LP boundedness of QMLE and QBE. Also, limit theorem of the estimator hold. And the limit is gamma inverse delta because our target random field Z is very simple. So this one. So the estimator should converge to gamma inverse delta. Okay, so if stochastic non-degeneracy of chi0, key index chi0, then we get the polynomial type large deviation. Okay, and by the theory, we get everything. So shall we get back to stochastic regression model? This is the Ito process with a unknown parameter theta in diffusion coefficient, and we have a finite time horizon, high frequency data. So it was the problem. And to estimate theta, in this situation, we can use this quasi-likelihood function. Here, S is matrix square of diffusion coefficient. So this is, okay? And delta Jy is J's increment of Y. So this is nothing but the local Gaussian approximation of transition probability of the process Y. So we use this H and theta. And in this situation, the limit random field Y theta has this representation. It is random because it involves process xt. And the key index, this is equivalent definition of the key index chi0. And if chi0 satisfies stochastic non-degeneracy, we get everything according to Khasminskii theory. For example, we get asymptotic mixed normality of QMLE and QBE. Okay. Limit is gamma minus half times zeta, and gamma is random matrix given here. And zeta is independent Gaussian, standard Gaussian random vector. And moreover, thanks to Khasminskii theory, we get convergence of the moments. So the problem is how to show how to verify such stochastic non-degeneracy of chi0, but it is possible. For example, we have two criteria for this inequality, so our problem is solved. We can do something similar even in asymptotic expansion. We consider the same model and the same data. And here, we consider asymptotic expansion of the estimator. Really we get such a estimate of error by approximation, error of approximation by density function Pn. So how to do it? So this is just combination of Ibaraki-Khasminskii theory. So that gives the LP estimate of various functionals. And if we combine that one to asymptotic expansion for martingales with a mixed normal limit, we can show such error bound. Or recently developed asymptotic expansion for scalar integral is also available. But anyway, LP estimate of the estimator, this one is very important in the proof. So this in this part, I want to discuss similar problem, but here we consider same martingale y, and unknown parameter is still in diffusion coefficient. But here we have a jump component, JT. And the capital T is fixed, so finite time horizon, and we have a high frequency data. Of course, we want to estimate theta from these data. This is a plot of increments of process Y. So you see quite often jumps occur. Before constructing estimated function, we consider a simple convergence of realized volatility of process Y. So as everyone knows, this converges to this limit, and we want to estimate theta, but of course the effect of jumps occurs here. So without removing jumps, we cannot estimate theta correctly. So we will construct a jump filter. Jump filter decides whether increment of y has jumps. More precisely, but before that, so classical approach. What is classical approach of jump filter? Classical approach uses deterministic threshold, constant times h2 power rho. Rho is constant in this interval, and h is discretization step. Delta jy is j's increment of y. And the classical approach, classical filter says if delta jy is bigger than this threshold, there are jumps. So this is the classical approach. It is nice because classical approach gives theoretically efficient estimator in any case. So in this sense, it is very nice. But in practice, if we use it to real data, the performance of the filter strongly depends on tuning parameter C and rho. And it becomes a big problem. To overcome this problem, we introduce a global filter. So here I'd like to explain what is global filter. First, we fix parameter delta 1. And with delta 1, we define number Sn in this way. So this means Sn is slightly smaller than the number of observations. And with Sn, alpha n is defined by this. And finally, alpha n becomes a rejection ratio. So we reject alpha n part of the data. Global filter is defined as follows. The set of so index set Kn. Index set Kn is a collection of J such that some variable Vj is less than some variable. Here I will explain. Here Vj is basically increment of y, but we put some initial estimator of plot volatility to make variable Vj. And we get V1 to Vn. And V raised J is J's order statistic. And so here we use SN's order statistic among these variables. And if Vj is smaller than this guy, we take that J. Otherwise, we reject J. So in this way, we make index set Kn. This is a global jump filter. And with Kn, we define random field Hn in this way. So basically, this is a local Gaussian approximation. So the idea is the same as before. But here, summation is not all J. Here, we put filter Kn. Pn and Qn are balancing constants. And you see Knj, but you can neglect it because it is quite near to 1. So this is basically a local Gaussian approximation. But we put global jump filter here. What is terrible here is this index set is very anticipative because it uses all the data. So martingale structure was completely destroyed by this index set. But finally, we can recover martingale structure by some procedure to get limit theorems. So anyway, we use this random field Hn theta. After that, everything is quite similar because we just use standard scheme coming from Khasminskii theory. For the present Hn, so this one with the global jump filter, of course, we define QMLE and QBE and make random field Zn from Hn. And in this situation, the limit random field Y has this expression. Seemingly, it is it is the same as before. It is the same random field that appeared in the case without jumps. So seemingly the same. And so the key index is the same. And if this key index is non-degenerate, in this sense, we get the polynomial type large deviation inequality for random field Zn, and by Khasminskii theory, LP boundedness of our estimators follow, and also limit theorem is obtained. So stable convergence of the estimator holds, and also by Khasminskii theory, we get LP moment convergence. So in summary, here we considered same martingale with jumps. And to estimate theta, we made a global jump filter and the random field Hn theta. So after that, we just follow the general scheme, we got everything. Yeah, today we only discussed a few problems, but so this scheme based on Khasminskii theory is very universal. So there are many applications already. This sheet gives some historic references in inference for diffusion process. And as for quasi-likelihood analysis, already quite a few papers given. There are many, so which so, for example, adaptive procedures can be made for. So this is what this is the ergodic diffusion process. Okay. So in that case, we can propose very complicated adaptive procedures for estimation of parameters. But finally, we can apply Khasminskii theory through the framework of quasi-likelihood analysis. So this is just one example, and so jump diffusion process, it is also the case. Even if an unknown parameter is in jump component, we can do something similar. And recently, Khasminskii theory through quasi-likelihood analysis was applied to, for example, information criteria. For example, Schwartz type models, Schwartz type information criterion that can be applied to dependent systems. And also recently, it was applied to regularization and sparse estimation. Also, we used the Khasminskii theory in the analysis of limit order. This is, how to say, this is a very practical object in finance. But still, we can apply their theory. So, yes, thank you very much for kind attention. This is my topic over.
Thank you very much, Professor Yoshida, for this interesting talk. So we have 5 minutes for some questions. Please write it in the chat window if you want to ask a question to Professor Yoshida. I have 2 questions for the moment. The first one is that in the classical, let's say, likelihood ratio theory, you have the possibility to get the properties of the maximum likelihood estimator, for instance, but we have also the possibility to write Ajek-Lecam Geganathan lower bounds for all kinds of estimators. Is it also the case in the QLA theory, or if you have mixing normal limit?
Okay. Yes. It is quite an important point. Yeah. First of all, how to say? So Hayek bound is very rigorous. I mean, it is based on the exact likelihood function. Yes. Exact likelihood function. On the other hand, yeah, for example, we are considering the discretely observed diffusion process, and so we have to use quasi-likelihood function. So this is not exactly likelihood function. So, but if we want to get Hayek bound, then we need exact likelihood function. And really, it is possible by using Marievan calculus. Of course, it is not done by ourselves. Yeah, for example, Bobet did it. And so, with exact likelihood function, yeah, for example, please. For example, this one. Yeah, so for simplicity, we consider diffusion process. So BT is function B of xt, for example. So in this case, transition density is written by Donska Watanabe's delta function. It is a very abstract expression, but it is exact. So we can show Hayek bound in a rigorous way. This is Gobet work. And so once we got the lower bound, then next step we can use Ibragimov-Khasminskii theory to estimate based on quasi-likelihood function. Okay, so estimator is not exact maximum likelihood estimator. It is quasi-maximum likelihood estimator, for example, but we can show it attains that exact Hayek lower bound of the risk. Okay.
Thank you, Professor Yoshida. So there is no other question, so we go through this session. Thank you.
Thank you very much.
The last speaker of this session is Rafail Z from the Weizmann Institute of Science.